Hello, today we're looking at using the compound angle formulae, which is going to involve two main things. It's going to involve us knowing how to use the compound angle formulae, but also knowing when to use the compound angle formulae, because as we know from this stage of maths by now, there are a lot less questions which are of the sort of type where they ask, use this particular method to do this particular thing, and it's often more of a case you get questions where they just present you with a problem and you have to decide for yourself what methods you're going to use to be able to get the answer. So to start things off, I can confirm these are the compound angle formula, and I can also confirm that they are in the formula booklet. This is also how they're written in the formula booklet. Worth and important knowing how to read them or use them when they're written in this form, because what you might see is they've got this plus minus symbol and also occasionally this minus plus symbol. And it's important we know how to use these properly. Because, for instance, if we're looking in the very first formula, the sign of a plus or minus b, if we want to have the formula for a plus b, we're picking the plus, which is on the top of the plus or minus symbol. If we've picked the symbol on the top there, that means in all the other plus or minus plus symbols, we always have to pick the top sign there as well. So if I'm picking sign of a plus b, it's got to be the plus over here as well, because the plus is on the top here. Whereas if I want the cos of a plus b formula, I've picked the plus, which is on the top here, but if you look on this symbol over here, it's a minus on the top. So if I'm doing cos of a plus b, I'm going to have cos of a cos b minus sine a sine b. And just to confirm on the last one, tan of a minus b, if I'm picking the minus, it's on the bottom, that would be tan of a minus tan of b divided by 1 plus tan a tan b, picking the symbols that are on the bottom throughout the entire formula in that case. Okay, now let's have a look at actually using it in a question. So first of all, here we have a prove the identity style question. And actually, I would say that despite identity questions often being questions students find more tricky, I would say that knowing when or when not to use the compound angle formula is actually slightly easier to do in the identity questions, because it all just boils down to looking at what's inside the trig functions in your identity. So if we look over here, we've got cos of theta plus 60. In the sine, we've got the theta plus 30 degrees, and then over here, we've got just a theta. That means that inside each of these trig functions, we've got different things. Now that's an issue because in a lot of the other identities we've come across, a lot of the things inside the trig functions are the same. For instance, if you're using sine squared x plus cos squared x equals 1, you'll notice it's an x in, or whatever you like, in both of the trig functions. It's the same thing in both trig functions. So this idea, well, in our particular identity we're looking at here, the fact we've got lots of different things in each of the trig functions, that's an issue. And that's where the compound angle formula will come in useful, because it will help us take these trig functions and be able to rewrite them in terms of smaller chunks, where each of those chunks will have more similar things in them. So let's go ahead and start doing that. We'll start by writing the compound angle formula for the cos theta plus 60 degrees. That would look like cos of theta, cos of times by cos of 60 degrees, minus sine of theta, sine of 60 degrees. And then we got to add on what sine of theta plus 30 degrees is. So that would be, using the compound angle for sine A plus B, that would be sine of theta cos of 30 degrees. That's a very dodgy S. Better. Plus sine of 30 degrees cos theta. And there we go. We've done the first step. Now, you might notice I'm not writing the cos theta, because remember, whenever we're proving an identity, it's worth pointing out you're only working on one side at the time. It's got to be a sort of case where you start on one side of the identity and work your way through until you reach the other side. So actually, to make this look a bit more posh and proper, let's start off by also having this line above it. Apologies, I should have already included this. Okay then, so next off we are going to then simplify what we've written here, because there are a number of things there that are just numbers. Cos of 60 degrees, that's just a number. Cos of 30 degrees, that's just a number. And so therefore we can rewrite them in their numerical form. So cos of 60, that's just going to be half. Then we've got sine of 60, which is root 3 over 2. And then we've also got cos of 30, and that's also root 3 over 2. And then we've also got a sine 30, and that's a half. Now, that has done exactly what we wanted when we used the compound angle formula, because what it's done is it's taken all these trig functions we had up here, which had lots of different things inside the trig functions, and now made it so we only have thetas inside all our trig functions, which is great, because it now means actually what we've got here can be simplified into something really nice. We notice we've got minus root 3 over 2 here, and we've got plus root 3 over 2 sine theta over here. So that means those two things are going to cancel out, leaving us just half cos theta plus half cos theta, which is just going to equal 1 cos theta. And there we go. We have proven the identity that we were expected to prove. So as I said, this actually wasn't the most difficult question, but I did think it highlighted quite clearly the reason of when it or when it isn't a good idea to use the compound angle formula. You're just looking for the trig functions to be having lots of different things inside them on the left-hand side versus what you have on the right-hand side. Okay, let's go on to the next thing. So the next thing is we're going to be looking at solving a trig equation. So the trig equation we've got here is like this. And straight away, we can see that we've got a sort of similar problem to what we had last time. It looks pretty complicated because you've got lots of different trig functions all in one equation, but then also inside the trig functions, we've got more than one different thing. We've got a cos 5x and a cos of x. We've got a sine of x. We've also got a sine of 5 of x. Now, this is a prime example of why, although the compound angle formula are in the formula booklet, it's really important that you're familiar with them, because if you're familiar with the compound angle formula, you might have got used to this idea that we've got cos of something times by cos of something else, and then a sine of that same thing times by that same sine of that other thing, which is one of the types of the compound angle formula we have. If we go back up to look at it, you might notice that this looks a lot like the compound angle formula for cos. And actually, as we specifically had a plus in between, it's very much like, if we're picking the plus on the bottom, it's very much like the cos of a minus b formula. So, putting that into practice, let's start off by factorizing the 14 out, just because that's making it look a bit more complicated. And I'll also write it in a more logical way, because on one bit we've got the 5x followed by the x, on the other side we've got the x followed by the 5x, which, I don't know, just seems a bit unnatural. So now it's written like this, it's a lot more obvious that yes, this is one of the compound angle formulas, and if we let a be our 5x and b be our x, then what we've got is cos of a minus b. So if a is equal to 5x and b is equal to x, we have cos of a minus b. So therefore, this entire thing can be written as cos of a, so our a is 5x, and our b is x. Oops. There you go. And that's equal to minus 7 root 3. Let's rewrite that as well. Cool. And then that can be simplified to just cos of 14 cos of 4x equals minus 7 root 3. And that is now an equation like you came across last year in first year of A-level content. You just want to first start off by dividing by 14, which ends up with that. And then beyond there, it's definitely all the other steps you've already come across. I'm not going to solve the rest of that equation. You could have a go at that yourself. I'll include the answers at the end of the video, so if you want to check how to do that, please do that. Or watch one of the other videos on how to solve trig equations of this type. Okay, so that was an example of a question where we took something that looked pretty complicated and then ended up being able to simplify it using the compound angle formula. Now, you might get some questions that are kind of the other way around. You might start with something that looks relatively simple at first glance, but you might want to use the compound angle formula to break it up so that you can then combine things and break things down. So an example of a question like that would be this. Question 3, solve 4 sine of theta minus 15 degrees equals root 2 cos of theta. So there are currently 2 issues that are making this question currently tricky to solve. The first thing is the classic, we've got more than one type of trig function. We've got the sine and we've got the cos there. And we know we preferably don't like that due to when we want to use the inverse trig functions, we only want to be there one type of trig function there. So that's something, but we've already dealt with that before in the first year. It's just a case of using a trig identity to convert between those two things. But as we said earlier, a lot of those identities that you've come across to be able to do that all involve having the same thing throughout. That's the issue we really experience here, because in one trig function we have theta minus 15 degrees, and in the other trig function we've just got a theta. And so that's our true problem, and that's what hints that perhaps we should be using the compound angle formula, because we need to deal with the fact that the trig functions have different things inside of them. So what we're going to start off by doing is we're going to use the compound angle formula to rewrite this expression on the left. So using the sine of a minus b compound angle formula, we write it as sine of theta cos of 15 degrees minus sine of 15 degrees cos of theta. And we haven't changed anything on the right hand side, so we're still going to write it there like that. Next, I'm going to multiply out the brackets and also put the cos 15 in front of the sine theta, just because cos 15 degrees is just a number. And we often like to write numbers in front of algebra. Now, as I already mentioned, cos of 15 degrees is just a number, sine of 15 degrees is a number, so you could, if you wanted to, type them into calculator to get them as a number, or if they turn out to be horrible decimals, then you could just leave them like this to write them in the exact form, but be aware that they are reality numbers, so you can treat them like numbers. However, in this particular case, actually cos of 15 degrees and sine of 15 degrees both come to okay-ish exact form numbers, so it's okay to write them as what the calculator says. Because if I write cos of 15 degrees, cos of 15 degrees comes to root 6 plus root 2 over 4. So when I times it by 4, we've got root 6 plus root 2. And that's how many lots of sine theta we therefore have. Similar sort of thing happening over here, except we'll end up with root 6 minus root 2, lots of cos theta, and of course we're taking that away. And on the right hand side, we've still got the root 2 cos theta. So good news, ultimately. We've ended up with now, we've still got 2 different types of trig functions. So we've got sines and coses, but they now only have thetas in. So it ended up just being approaching this question like we have had done previously in the first year. I'm going to gather the cos thetas together first of all. So I'm going to add root 6 minus root 2 lots of cos theta onto both sides. And of course, we realise at this point we can simplify it because we've got root 2 cos theta plus root 6 minus root 2 cos theta. So the root 2's are going to cancel out there, leaving us with this. And now I notice I've got a sine theta, I've got a cos theta. I'm thinking, is there any trig identity involving both of them? Of course, we've got the classic sine theta divided by cos theta equals tan theta. And this is going to be a prime good use of that identity, because to get tan theta, all we've got to do is divide by cos theta now. And because there's no extra pesky numbers being added on anywhere, we're not going to end up dividing anything by cos theta that we don't want to. So if we do that, got to remember the brackets around that stuff. And then also I could divide by root 6 root 2. So if I do that, I'm going to be left with just tan theta on the left hand side, and on the right hand side root 6 over root 6 plus root 2. And that is now, again, one of the base level trigonometric equations to solve, because we've just got a single trig function equals a number. And that will be using the skills you've learned before. So have a go at finishing that question off if you want. Okay, so I've now shown you a few different ways in which you can use the compound angle formula. Sometimes, as I said before, you might be wanting to take something complicated and simplify it, and other times you might want to be taking something and sort of splitting it up, breaking it down to small chunks so you can then combine or simplify things. It's worth reminding you one last time before you go that you can't multiply out the brackets if you have, for instance, cos of x plus 10. Cos is not a number, it's a function, and same for all the other trig functions, and therefore you can't multiply the brackets because there is nothing to multiply. And instead, this is what the compound angle formula for, therefore effectively a replacement for that process. Okay then, last thing to leave you with is the answers, the numerical answers to question 2 and question 3, in case you had a go at them yourself all the way through to the end. And with that, I'm done. Have a lovely day.